I'm John Doherty. Thanks for joining me. This video explores the question of just what is the calibrated model? What can it deliver? What can't it deliver? And how should it be used in decision support? During this video, I'd like to explore the question of what is the calibrated model really mean? What does model calibration achieve for a model that's used to make decisions? And how should the calibrated model be treated when it's used in the decision-making process? A lot of store is put in the calibrated model. It is the outcome of a lot of work that supports important environmental decisions. And reports that describe modelling work often include plots such as this. Plots that show a good fit between model outputs and field measurements, either head measurements, production measurements, flux measurements. And those reports will often include figures such as the ones I'm showing you here, where we have plots of modelled versus measured. And the closer they are, the dots are to the one-to-one line, the better is the model calibrated. So it's said. Statistics will often accompany these plots, RMS for example. And ideally, the better is the RMS fit, the better is the model in terms of being calibrated, and by implication, the better is the model in terms of the support that it can provide to the decision-making process. Personally, I do not like plots such as this. They don't tell me much at all. They don't tell me exactly how well the model is doing in replicating the past behaviour of the system. They don't tell me any of its possible inadequacies that might point to defects in its simulation of the future behaviour of a system. However, they're commonly used, but, as I say, in my opinion, fairly uninformative. But we've got to ask more than just how well is a model calibrated, with the implication being that a good fit in the past means there'll be a good fit with the future. Things are more complicated than that. We know that the world, that the earth, the medium through which water flows, is heterogeneous at every scale. We know that hydraulic conductivity can vary by orders of magnitude. We know that every aspect that governs the movement of groundwater and of contaminants contained therein is complicated. The Earth is complicated just to look at from a satellite or from an aeroplane. The geology is complicated to look at in outcrop. Recharge patterns are complicated. They depend on land use, topography, rainfall, where the water lies after rainfall. And history matching is never going to provide a unique estimate of all the properties of a system that is this complicated. So even if we do get a good fit between model outputs and field data, we still have a problem that the possibility of unique inference of all the hydraulic properties in all the places within a model domain is completely impossible. Yet, we sign up for a calibrated model. A lot of store is put in the outputs of a calibrated model, and implied in the word calibration is uniqueness. And it's obvious that uniqueness cannot possibly exist when it comes to a groundwater model. So, we have a paradox here. We have a paradox that we sign up for uniqueness the moment we sign up for a calibrated model, yet it's impossible to infer the hydraulic properties of the system which we're simulating with uniqueness. That means that if I were to get a good calibrated model, if I were to get a nice low RMS and have hydraulic properties that are reasonable, I'd have a certain set of parameters. And if a colleague was to do the same when calibrating his or her model, he or she would have a different set of parameters. Which one should we use to make a prediction? But if we're signing up for a unique parameter field, we've got to do better than that. There has to be some condition that creates uniqueness, which conceptually both me and my colleague could use to achieve the same unique parameter field. And what is this concept then? Well, it can be shown, mathematically it can be shown that a certain set of constraints can be applied to the history matching process, which will not only give us uniqueness of the parameter field, but will give us uniqueness in a way that matters most for a model that we're going to use to make important predictions. And those conditions, those constraints that are applied to the parameters that are estimated through the calibration process are that the solution to the inverse problem that we solve when we're calibrating a model, the solution to that problem is of minimum error variance. That is, we ask and we constrain parameters to adopt values that firstly are realistic, secondly allow us to fit the historical behaviour of the system, and thirdly are estimates of the values of hydraulic properties which are minimally wrong. That is, of minimal error variance, minimized error variance. And by minimizing the error variance of all parameters of a model, we minimize the error variance of any prediction that a model has to make. This then gives us a pleasing outcome for the calibration process, an important outcome for the calibration process, and it also gives us that important quality of uniqueness which the calibration process must seek if we're going to come up with a single parameter field which we're then going to use to make predictions. Well, that is pleasing, for these considerations inform us that calibration as a concept makes sense. However, just because we can, in theory, arrive at a parameter field that allows us to make predictions which are of minimized error variance, unfortunately this does not mean that the error variance of some predictions made by a calibrated model will not be large. To illustrate this, let's look at a case that was explored by a student of mine quite a few years ago. Here we have a synthetic model. We have water flowing in at the top of the system, and we have a fixed head at the bottom of the system. And a particle I'm going to release near the top of the model domain, and it's going to be carried with the water to the bottom of the model domain through a heterogeneous hydraulic conductivity field which I generate using a random parameter field generator, a multi-Gaussian random parameter field generator. So I know reality in this case because reality is synthetic. As well as being able to simulate the movement of the particle, I can simulate heads at every cell in the model domain. And from those heads I can generate a calibration data set. So there's the answer at the back of the book. That's how long it takes the particle to reach the bottom of the system. And now I'm going to make that same prediction with a calibrated parameter field, where I calibrate that parameter field using different numbers of heads in different numbers of notional wells spread throughout the model domain. So the synthetic model calculates heads. I then back calculate hydraulic properties from those heads, in this case hydraulic conductivity, and I make the prediction of my particle travel time using the inferred parameter field. And, in ways we'll talk about in other videos, I do everything correctly. I seek and achieve a minimum error variance solution to the inverse problem of model calibration. So I use 84 head observations, 42, 24, 18 and 12. There's reality once again. Here is the parameter field that emerges from calibration against 84 heads. We can see that it's a somewhat subdued form of reality that arises through the calibration process. And here is the calibrated parameter field that emerges from an ever-decreasing number of well observations, head observations. The less observations I use, the more blurry does the calibrated parameter field become. And, looking at this, the more wrong does the prediction of the particle travel time become. So here, my perfectly calibrated model is making a prediction which is 100% wrong. Now when we think about it, that's not too surprising. The time it takes for that particle to reach the bottom of the system is sensitive to hydraulic property detail, but it is impossible to capture that detail from a mere 12 head observations. Hence, we have a very subdued reflection of reality in the calibrated parameter field that emerges from 12 head observations. It makes sense that the prediction made by that of where that particle emerges, the prediction made by that calibrated model may actually be wrong. If I had used different random parameter fields and repeated this whole exercise, I may not be as wrong, or I may have been wrong in the opposite direction. So it depends, the extent to which I'm wrong will depend on the parameter field used in this exercise. But the same problem remains. The detail on which that prediction depends is beyond my reach when I'm inferring details of hydraulic properties through a calibration process. Therefore, any prediction which depends on those details has the potential for error. I've minimized that potential for error, however, I cannot eliminate it, and how far I can minimize is dependent on the information content of the calibration data set. That sets the minimum extent to which I can minimize the potential error of any prediction I make. That sets the minimum uncertainty of the prediction I make, and that's just something with which I have to live. So how can we understand this a little bit better? Because through understanding it, we can learn more about what calibration can and cannot achieve, and therefore learn more about how we should use a calibrated model when making a prediction of management interest. One very informative way to look at the whole history matching process is through the eyes of singular value decomposition. Now, singular value decomposition is something used a lot in linear algebra. That'll be discussed in other videos. For the moment, let's just look at what it can tell us about the history matching process. Notionally, reality is a vector in a high-dimensional parameter space. All the parameters in any model that we build, the hydraulic properties are going to be different in every cell of a model domain because that's the nature of reality. It is heterogeneous. And the collection of numbers that represents the values of parameters in all of those cells we can put into one single bundle of numbers called a vector, and our task is to estimate that vector through back calculation of it from another vector, that vector being the values of observations that comprise a calibration data set. Reality then is a vector in a very high dimensional parameter space. Singular value decomposition tells us that the best I can hope for in back calculating parameters is not reality, because reality is not mine to know. I will never know reality. The best I can hope to capture of reality is the projection of reality onto a much smaller dimensional subspace, called the solution space in this picture. And the dimensions of that subspace can be no more than the number of observations comprising the calibration data set, often much less. So, what I can infer through calibration is a shadow, a reflection of reality. However, I even get that wrong, because measurements that comprise the calibration data set have noise. The solution to the inverse problem, the calibrated parameter set, inherits that noise. So, my estimates of that shadow will be a little bit wrong because of it. The error in my parameters is the sum, then, of two contributions to wrongness, that born of noise in the data, but often in the groundwater modelling context, the biggest contribution to errors in parameters is the fact that I can only estimate a very small subspace of what parameters really are, just a small dimensional shadow of reality. And to the extent that any prediction that I care about is sensitive to the detail, that is, the things that are beyond the reach of the parameter estimation process, to that extent, those predictions may be wrong. And I have to recognize that potential for wrongness when I use the model to make a prediction, and when I'm seeking this unique fabricated thing called the calibrated model, I have to minimize that potential for wrongness. Singular value decomposition tells us that the way to minimize that potential wrongness is to stay in the solution space. Reality could be up here, it could be down there. Stay in the solution space by only including as much heterogeneity in the calibrated parameter field as the calibration data set can actually inform, guarantees that I've minimized my potential for predictive error and my potential for predictive error in parameters and in the prediction through making that potential symmetrical with respect to the parameters and the prediction that I make, and I do that by staying right here in the solution space, by not including anything in the estimated parameter field that cannot be justified by information in the calibration data set. The result, as we have seen, is a subdued form of reality, a shadow of reality on a small dimensional space. Gives me a good fit with the data, but the difference between the parameter field that I come up with and reality could be very large indeed. But I have minimized my potential for parameter and predictive error by adopting that course of model calibration. So singular value decomposition tells us that if we want uniqueness, there's a price to be paid. It's an abstract parameter field, a shadow of reality that has considerable error, but unknown error, but I can guarantee that if I do everything correctly, I've minimized the potential for error in the calibrated parameter field and any predictions that are sensitive to that calibrated parameter field, as all are. Another way to look at this process is through the eyes of Bayes' equation. And Bayes' equation is really the last word on history matching. Bayes' equation says that we start off with a prior probability distribution of parameters. This is our expert knowledge at work, supplemented maybe with some direct measurements of hydraulic properties. The prior probability distribution then it is an expression of our expert knowledge and an expression of the fact that our expert knowledge is limited. We don't know what's under the ground. We do know what's not under the ground. And between the upper and lower bounds of what we don't know, there are an awful lot of possibilities. And from a prior probability distribution, we can notionally generate realizations of reality as it may exist under the ground. And any one of those realizations can include an awful lot of detail. The fact that hydraulic properties are so heterogeneous, the fact that we don't know where every layer of every geology type is, we don't know where the faults are and what their throws are. So the prior probability distribution leaves open a lot of possibilities. But not everything that we can imagine exists under the ground may actually be usable by the model when we use that model to make predictions, because not every realization of what we imagine will allow the model to replicate the past behavior of the system. That is, it won't allow the model to fit the calibration data set. So this term here in Bayes' equation is called the likelihood function. Here I'm representing my unknown parameters by the vector k. I'm representing my observations by the vector h. This likelihood function says that the better that the model outputs fit the data, the better I like the parameter field. So we take our prior probability distribution in a kind of a journey here through a workflow. We take the prior probability distribution, filter that prior probability distribution by accepting only realizations of reality which allow the model outputs to fit the calibration data set, to end up with a posterior probability distribution. Bayes' equation makes abundant conceptual sense. In practice, it's difficult to implement numerically, but we'll put that problem aside for the moment. Meanwhile, Bayes' equation tells us that I start off with uncertainty and I finish with uncertainty. For some predictions, the imposition of calibration constraints, the fact that I have to replicate the past, allows for a narrower uncertainty associated with some predictions, possibly not with others. But the bottom line is there will be uncertainty associated with any prediction made by a calibrated model. Well, let me rephrase that, by a history-matched model. What then is the calibrated model? If we're going to follow the precepts that we just talked about, if we're going to seek uniqueness instead of a posterior probability distribution, we have to seek a parameter field that gives us minimum error variance solution to that inverse problem. That is, the parameter field which is somewhere near the center of the posterior parameter probability distribution, and when I make a prediction, it gives me predictions that are somewhere near the center of the posterior predictive probability distribution. This is what I seek when I seek uniqueness. However, this does beg the question, maybe I can justify that I'm near the center of the posterior predictive probability distribution, but what am I near the center of? This, or this, or this? So there's a certain amount of dissatisfaction in just making a prediction with a calibrated model, because if there's some bad thing out here that I don't want to happen when I manage the system, the prediction made with the calibrated model may indeed give me the prediction where I've minimized my potential for wrongness, but if that potential for wrongness is still high, if it's still large, I may not be able to rule out the possibility that something that I don't want to happen can indeed happen. And I need to know that if I'm going to base my management of a certain area on predictions made by this model. So what are the repercussions of this for decision support modelling? We know that predictions made by a calibrated model are going to be in error. We know that conceptually at least we can minimise that error by coming up with a calibrated parameter field that gives predictions of minimum error variance. But we should also be realising by now that that is not the end of the story when constructing a model that we're going to use as a basis for decision support. We should also realise by now that we should never expect a model to make correct predictions. That's out of the question. The metrics then by which we should judge a model that's going to be used to support decisions is not that it makes a correct prediction, because that will never happen. It's that the correct prediction, which we will never know, lies within the uncertainty limits that conceptually we can actually calculate using a model. And the other metric for a model that we use for decision support is that we try to reduce those uncertainty limits to the extent we need to make a decision. Sometimes that will be to the minimum that the information content of the calibration data set allows. Sometimes it will be just enough to rule out the possibilities that certain bad things will happen. But the main point here is this. Just because a model's calibrated, it doesn't mean that it's going to make a correct prediction. It means it's going to make a prediction for which the potential for incorrectness has been minimized. However, that potential may still be very high, and part of the decision support modeling process has to be some attempt to quantify the uncertainty of that prediction, notwithstanding the fact that we've minimized the potential for that prediction to be wrong through calibrating that model in ways that try to achieve that minimum error variance solution to the inverse problem. So given what I've just said, it's valid to ask the question, why calibrate a model? History match, yes, but why seek uniqueness? Why seek a minimum error variance solution to the inverse problem when what we obtain is a subdued form of reality that is not reality, that whose potential for error has been minimized, but which still has a lot of error? Why not directly implement Bayes' equation? And using modern methods such as ensemble smoothers, we can actually do this. Well, we can approximately do it. Nothing can actually implement Bayes' equation perfectly in the very high dimensional parameter world in which we live when we're history matching a groundwater model. Still, there are methods available which, in theory at least, allow us to actually sample the posterior probability distribution. That is, we come up with not one, but a whole ensemble of parameter fields, all of which are realistic to a point, and all of which allow the model to replicate the historical behavior of the system. When we make a prediction, we then make a prediction with all of these parameter fields. And that way, we haven't got to come up with an abstract, simplified parameter field which doesn't actually look real, which is actually an abstraction. Now there's quite a valid argument to say, let's not calibrate, let's just go straight to Bayes' equation. However, there are still some arguments for doing calibration, for coming up with a minimum error variance solution to the inverse problem, notwithstanding the somewhat abstract nature of the parameter field that we come up with. I've just got 4 here. The first one is that normally when we're calibrating a model, we're just in the process of constructing a model. Often we're not terribly sure that the concepts on which we're building that model are correct. And so the calibration process, the history matching process, is in some ways a process of testing hypotheses. We're seeing if we can fit the historical behaviour of the system given the concepts that are underpinning the model. If we can't, we need to revise those concepts. And given the exploratory nature of the history matching process that we're undertaking, it will often get confusing if we're doing this with random parameter fields. It often makes sense to introduce into this hypothesis testing process only as much heterogeneity as the data set allows, and if it's too much, obviously parameters are taking on surrogate roles, obviously our concepts are wrong, and this becomes clear if we're just seeking a minimum error variance solution to the inverse problem. Another reason that we may undertake traditional calibration is that we get pretty good fits with the data if our model is a good model and if our concepts that underpin that model are good, and if the data is good, of course. If we're going to use that model to predict the future behaviour of the system in ways that resemble very much the measurements that we have of the historical behaviour of the system, then being able to reproduce the past will lower the uncertainty of predictions of the future. The error variance of future predictions may not be too great, and using modern inversion methods we can fit the past pretty well if all the conditions are right, including the fact that the data is of high quality. Another case for traditional history matching, seeking uniqueness through calibration, is that some of the ancillary information that we get from that process, for example, parameter sensitivities, can be used to undertake linear analysis. And that linear analysis can help us quantify the uncertainties of predictions of management interest. It can be used to track the flow of data from observations to parameters and then to the prediction. It can be used to assess the comparative worth of different data types that collectively comprise the calibration data set. And this is a nice little byproduct of the history matching process. And lastly, if we're going to use modelling to test hypotheses about specific predictions made by the model, that way if we're going to use the model as a scientific instrument to investigate whether certain things that we don't want to happen in the future can in fact still happen, notwithstanding all the information we have at our disposal through expert knowledge and the historical behaviour of the system, then traditional calibration, traditional seeking of a unique minimum error variance solution to the parameter field is a necessary prerequisite for using the model in a predictive hypothesis testing capacity. So yes, there are times when calibration is the best thing to do, but we always have to remember though that calibration has to be done in a way that purposefully seeks a minimum error variance solution to the inverse problem, and that just because we've minimized the potential for error in any prediction we make with that calibrated model, this does not mean that that potential for error will not be high. And if the model is going to be used to make predictions of management interest, that potential has to be explored if modelling is going to support the decision support process correctly. Thank you.